Homeostasis. This lecture series will focus on homeostasis, which I told you is one of the main themes of anatomy and physiology. Come back many times throughout the year. I'm also going to talk about rapid change because I want to be able to contrast negative and positive feedback, which are different things. So first, I want to start by talking about homeostasis. Here's my screen. What is homeostasis? See if you can define this yourself. It is the maintenance of a relatively constant internal environment. You don't need to memorize this exact term, but I want you to understand it, right? So we're maintaining fairly stable variables inside the body. So internal environment, and it needs to be relatively constant. What does that mean? It's not just completely steady. There's some dynamicness to it. So there's some oscillations, there's a range. And we'll see examples of this. But this represents negative feedback happening. So as your body is trying to maintain homeostasis, and as things are happening, body processes are happening and different organ systems are doing different things, relatively constant is as good as we can get. Just like a thermostat in your house probably doesn't always feel perfect. So we need to be able to maintain these certain variables in our body within relatively stable states. What are regulated variables? Well, it's something that needs to be maintained. So something that can be detected, we need to be able to detect it, be able to address issues with it, and then maintained close to the set point. So regulated variables are maintained within a range that allows for our bodies to function properly. Not everything in our body is a regulated variable, not everything produced or active. There's certain requirements. So think about what are some things our bodies do strive to maintain within normal ranges. Okay, here's some core body temperature, right? Our bodies get too hot or too cold. We have dysfunction and disease occur. We are constantly, our bodies are trying to keep our temperatures around 98 degrees. Blood pressure, blood volume, and blood osmolarity are actually three separately regulated variables. They're all closely related to each other in terms of how they affect one another, but they are, what we'll get to in the spring. For example, blood pressure is regulated, detected by baroreceptors, like a barometer, and blood osmolarity is detected by osmoreceptors. So they're actually different mechanisms of proteins that we'll talk about some of those different proteins later. So those are all three different variables that our body's constantly trying to maintain that are often related to each other. Blood glucose. So glucose levels, you can get hangry if glucose gets too low. Other nutrients as well in the blood that we want to have a constant supply, especially to the brain. Your brain only uses glucose. It cannot break down other nutrients like the rest of your body can. So that's actually the reason blood glucose is so important to maintain, because if your neurons can't function or start to die, that's a bad thing. Okay, the last two are closely related. pH is hydrogen ions, so that's a type of inorganic ion. These are all ions that either are important for our bodies to function: sodium, chloride, potassium. Hydrogen ions are important, and also too low of a pH can cause proteins to denature. So we want to keep that within normal ranges. What about things, an example of something that's not, so heart rate. Is that a regulated variable? Is that something we need to keep within a narrow range with some maybe oscillation around it? No, right? So heart rate is designed to very dramatically change in order to maintain oxygen and glucose levels to the various, and heart rate regulates a lot of stuff. It's regulating carbon dioxide as well. So heart rate changes dramatically in order to maintain the regulated variables that are listed here. So things like pH, oxygen and carbon dioxide, glucose, blood pressure, right? Heart rate regulates blood pressure. it itself is not a regulated variable. That's one example of something in our body that happens, heart beats, that's really important, but itself is not a regulated variable. Your heart rate can range in a single person from 40 while you're sleeping, 40 beats per minute, to close to 200 if you do intense exercise. That's a huge range. That's not a homeostatic variable. So back to homeostasis, it refers to the maintenance of a range in all environmental conditions. And it's not equal to equilibrium. So homeostasis does not mean equilibrium. First example of that, body temperature, right? Our body temperatures are never the same as the external body temperature. In fact, when it's 98 degrees out, our bodies are suffering, partially because we're always generating heat. So we want to be able to put that heat out into the world. But outside does not equal inside. Homeostasis does not mean the same. It means often disequilibrium. And that's why homeostasis takes work. It takes work to maintain the inside of our bodies different than the outside, or the inside of our cells different than the outside. So another example of that is ion concentrations. This graph here shows ion concentrations in the extracellular fluid, or ECF, and then in the intracellular fluid, or ICF. So I want you to look at these ion concentrations, sodium, chloride, potassium. How does this graph, this is concentration here on the y-axis, exemplify that homeostasis doesn't mean equilibrium? Pause and answer that for me. All right, so idea here is that these ions are not in equilibrium. This is normal. This is how the cell is supposed to be. High sodium and chloride on the outside of the cell, high potassium on the inside of the cell. That's how it's got to be. And we'll really see this when we talk about neural function, how important this is to maintain this disequilibrium. So the ion concentrations have to be within a normal range. You've got to have outside of the cells around 140 micromoles of sodium, or you're going to have some problems. Inside of the cell has to have about 140 millimoles of potassium. You're going to have some problems. However, it's not equilibrium. You must maintain these unequal concentrations inside and out of the cell. And that's homeostasis means maintaining, not maintaining equal. So this maintaining, again, takes energy. It takes energy to, and well, literally in this case, it's the sodium-potassium pump that's pumping sodium out and pumping potassium in, that's creating this disequilibrium. Another example, though, is it takes work, like sweating, right? To cool off, you need to sweat. That's a process that takes work. We'll come back to ion concentrations more in the future. So what I want to do is try to draw for you what this looks like over time. So going back to the idea of dynamic states opposed to steady state. So this is body temperature, and I'm still getting better at, well, I'm working on getting better at this. Body temperature, 98 degrees Fahrenheit, about 37 degrees Celsius. That's our set point. And that's somewhat variable for different people. This is our y-axis is temperature, x-axis is time. So temperature is dependent on our time, changes over time. How does our temperature actually go? It does not follow along this line perfectly. It goes up and down. Beautiful artwork there. So this is our fluctuations around the set point. There's a range of normal function. This is normal. These oscillations are normal that occur around the set point. And it's homeostatic processes that maintain this. There's going to be negative feedback that acts at both of these points, top and bottom, and really all the time in balance to maintain this. And we'll see this more in detail when I get to negative feedback. We'll look at this. But just to give you a little concrete right now, here with body temperature up at the top here, if you're getting too hot, you're gonna start sweating. That's gonna bring you down to here. Down, you get too cold, you might first thing feel cold, put a sweater on. You might start shivering if you get real cold. producing more ATP to increase that body temperature back up again. Vasodilation and vasoconstriction are two other ways that commonly happens. So let's actually go over to a better picture of this idea of dynamic equilibrium. It's not a steady state. So this is the same thing I just showed with temperature on the y-axis. However, it has a set point as 30 degrees Celsius. Don't actually quite know why, because 37 is what it should be. Anyways, there's a set point. Doesn't matter what it is. Maybe it's a different organism that has a lower body temperature. So there's a set point, and then you've got these fluctuations or oscillations that represent the normal range of function. The internal conditions must be maintained around this fairly narrow range. Regardless of summer, winter, we're sitting, we're exercising, set points can change a little bit. So when you're exercising, you actually have a slightly higher set point. It's kind of a different thing. So homeostasis, literally the word homeo means unchanging, but it's actually a dynamic state. And again, if these variables aren't maintained, so temperature, pH, ion concentrations, dysfunction or disease can occur. So that's why this is so important. One last thing here for the introduction. So these organ systems are all acting to maintain homeostasis. But that's not all they do, right? They're all trying to do their thing. The digestive system, it's trying to get nutrients. When it does that, it's maybe creating some unbalance somewhere else. So it's always a balance between different organ systems. Also, body systems need to carry out processes. Digestion is a process. Childbirth is a good one here, so reproductive system, a process. So organ systems aren't always just maintaining homeostasis, and that's where the rapid change comes in. So I'll talk about positive feedback as well in terms of loops is part of this lecture as well, which is different than maintaining homeostasis. Our bodies need to actually just do things too, not just maintain. So the learning outcome for this was define homeostasis and explain why this concept is central to physiology. Some of the terms that we used here, again, dynamic equilibrium representing those fluctuations opposed to a steady state, versus disequilibrium referring to the idea that there are differences that are being maintained. So, and that those terms aren't particularly important, besides that it helps, I want you to understand the concepts behind both dynamic equilibrium and disequilibrium. All right, stay tuned.